Okay, so we'll add a third example to this list now, and this is the function that we're going to consider. So I'm going to take the limit as x approaches 1 of x minus 1 divided by the square root of x minus 1. Now this is another function that is built from the functions that we gave in our previous list, right? We've got a fraction. The numerator is x minus 1. Well, that's a polynomial. The denominator is the square root of x minus 1. Well, the square root, that's a radical symbol, so radical functions are continuous, and then we put them together as a fraction, so the result is going to be continuous on its domain. However, this example differs from our previous two, and by the previous two I mean the 1 and 2 that we did immediately at the bottom of the previous page. And what I mean by that is, well, what happens if you run through the process of just plugging 1 into the function? What you're going to find is that 1 is actually not in its domain, right? And in fact, it's a 0 over 0 type, because if I plug in 1, I'm going to get 0, or I'm going to get 1 minus 1 on the numerator, which is 0, and I'll get the square root of 1 minus 1, which is also 0 on the denominator. So it's a 0 over 0 type. So simply plugging in the number x equals 1 is not going to cut it for this example. So we'll have to try something else. And for this particular problem, it's not obvious what to do until someone shows you the trick, because you can't do any canceling here in its current form. But what you can do is make the observation that x minus 1 is actually the following. I can write it as the square root of x squared minus 1 squared. Now, why do you think I would want to do that? Well, now it's a difference of squares. So we can use the special factoring formula to write this as root x minus 1 times root x plus 1, right? And then that, if we apply that to our limit now, let's substitute this expression in for x minus 1 in our numerator. So we're going to get the limit as x approaches 1 of root x minus 1 root x plus 1 all over the root x minus 1 that was already there. And now you can see that common factor, right? We had a common factor of root x minus 1, which we can cancel. Okay, and that gives us now the limit as x approaches 1 of the square root of x plus 1. And that is a continuous function on its domain, right? This is still a continuous function, and this is a continuous function that happens to be defined at the point 1. So now if we plug in x equals 1, we get a finite value. We get the square root of 1 plus 1, which is 2. So that's how we can work that limit out. So that's an algebraic solution to that problem. So this function is continuous, but it's not defined at 1. This function is continuous, and it is defined at 1. And this function agree at every single point except x equals 1. So that's why we were able to do that substitution, or function replacement, if you will, right? We were able to consider this function in our limit instead of this one. Okay, let's draw a picture of this, because this is actually a good opportunity to introduce an idea, which is what we'll talk about in the immediate section below. If I draw a sketch of this function, and if you, depending on where you're looking, you might look at this and think, man, how are we going to get a graph of this function without software to help us? Or if you're looking at this function, this looks very difficult to graph. But if you look over here, remember, this function and this function are equal at every point except x equals 1. So it may be helpful to look over here, and this is the square root of x plus 1. Well, the square root of x is just the top half of a sideways facing parabola. It opens to the right. And if you add 1, you're really just going to shift the whole thing up by 1 unit. So let's draw point 1 on the y-axis. Really, this is the picture you have. You've got this curve, right? And except right at x equals 1, there's a hole, which I could have probably drawn a bit better, but there's a hole in the graph right at x equals 1, right? Because we're really graphing this function. This is the graph of y equals x minus 1 over root x minus 1. I just want to be clear. I'm graphing this function here, not this one. We're graphing this function. It just turns out that this function looks almost exactly the same as this one, and this one's easier to graph. So that's why we looked at this one to get the curve. But then when you consider the fact that you're actually dealing with this function, you have to remember that you're not actually defined at x equals 1. So this is a hole. So we have a hole in this graph. And that's one of the ways a function can be discontinuous at a certain point. It could have a hole in it. And having a hole is really, formally this is referred to as a removable discontinuity. And that's what we're going to define below. So in part 3, so in other words, this example is what I'm, pardon me, when I say in part 3 down here, I'm really just referring to this example or this graph. So this is an example of a function with a removable discontinuity. Now, this is actually a phrase that gets misunderstood sometimes, so let me clarify. When we call it a removable discontinuity, it makes it sound really harmless, right? It makes it sound like we almost don't even need to be worried about it and we can pretend that it's not a problem, but it is a problem. This function is not continuous at x equals 1, so why do we call it removable discontinuity? Think about it this way. If someone came along and they said, okay, I want to make a new function that behaves exactly like this, with the exception that it's actually defined at 1 and it's continuous at 1. Well, you could easily do that. Just plug the hole, right? Just shade that hole. And really, algebraically, that's essentially what we did here, right? We instead of working with this function, we worked with this one instead. And this is essentially what you would get if you plug that hole. You would get this function here. So because it's so possible to do that, right? You can imagine there's other situations where it's not so simple to repair the discontinuity. You can't just simply shade in a single point and fix the problem. But in this case, you could. So that's why it's called a removable discontinuity. But just be clear, just because you could shade in the hole doesn't mean that hole isn't there right now. So it is still a discontinuity. Okay, and in general, how do you detect a removable discontinuity? So without having to refer to the picture. Well, here's the definition. So a point, if you have a real number a, such that, first of all, the function f is not continuous at the point x equals a, but you do have the property that the limit as x approaches a of f of x exists. In other words, the limit from the left is equal to the limit from the right. You do still have that these two quantities both exist and are equal, but it turns out that the function's not continuous at x equals a. So in other words, another way to think about it, if we were to go back to the definition of continuity at a particular point, x equals a, imagine if you worked out all three of these quantities and the outside two were equal and agreed. But the middle one, either it was some different value or maybe it wasn't defined at all. That's the situation that we're describing down here when we say the definition of a removable discontinuity. That's what this is describing. Okay, so that's one type of discontinuity, and in fact there are three different types of discontinuities. So another type of discontinuity, we've already seen these before, we just didn't call them infinite, we just didn't call them discontinuities, are infinite discontinuities. So we're actually going to revisit the idea of infinite limits down here. I'm going to give you an example of calculating one algebraically, without the graph, in other words. So here's the definition. An infinite discontinuity occurs wherever a function has a vertical asymptote. So that's another way you can have a function with a discontinuity. If it explodes in the positive direction or in the negative direction near a particular point on the x-axis. That's what it means to have a vertical asymptote, right? And whenever that happens, we say that the function has an infinite discontinuity at that point. Okay, here's an example. The function f of x, which is given by 2x plus 2 over x minus 1, this function has an infinite discontinuity at the point x equals 1. Because, and then we've left room to justify it down below. Now, some people look at this and say, oh, of course it does. Because if I plug in x equals 1, I get 0 on the denominator. And that's a really crude, kind of a not very formal way to justify this, and it's not very convincing. So, because what does it mean to have a vertical asymptote? Well, it means that the limit as x gets, well, in this case, if I'm claiming there's an infinite discontinuity at x equals 1, really, to justify that, I have to show that there's a vertical asymptote at x equals 1. And remember that vertical asymptotes happen whenever the limit as x gets close to a value, either from the left or the right, the function either blows up to positive infinity or negative infinity. Okay, and if you don't remember, just pause this and go back to section 2.2 and just quickly look up the definition of a vertical asymptote in the notes, and you'll see that. Okay, so we need to verify that the function, this function here, either goes to positive infinity or negative infinity as x gets close to this point, either from the left or the right. Either one will do. So let's just pick a direction. Let's just take the limit as x approaches 1 of the function f of x, but we'll take the limit as x approaches 1 from the left. You could also take it from the right. There's no reason you have to do from the left here, but you have to pick a direction for this technique to work. So that's why I'm going to pick from the left. Okay, so, well, limit as x approaches 1 from the left of f of x, this is going to be the limit as x approaches 1 from the left of 2x plus 2 over x minus 1. Okay, so that's just what f of x is. Okay, so how do you proceed here now? Well, what you want to do this carefully, look at each piece separately. If I just look at the numerator, 2x plus 2, what happens as x gets closer and closer to 1? Well, and you don't even really need to consider the fact that x is getting closer to 1 from the left here, because you can still see as x gets close to 1, the numerator is going to get close to 4, right? This is going to get closer and closer to 2 times 1 plus 1, which is just 2 plus 2, which is 4. So the numerator is actually approaching 4. What about the denominator? What's happening to the denominator now? Let's draw a little bubble around that. What's happening to x minus 1 as x gets really close to 1 from the left? Well, as x gets close to 1 from the left, it's getting close to 1, but the value of x is less than 1. That's important here. Because if you look at the expression x minus 1, you're subtracting 1 from x. And if x happens to be a value that's less than 1, and you subtract 1 from something smaller than 1, you're going to get a negative value, right? And of course, as x gets closer and closer to 1, the denominator is approaching 0. We know that it's approaching 0. But if we know also that the values of x minus 1 are negative, we know it's approaching 0 from the left. This is the notation that I'll use to communicate that. Okay, so if that didn't make sense that much, think about it this way. Okay, here's a way you can do it by hand. Instead of going, you don't have to necessarily go through the same logic that I just did. Think about it this way. You've got x approaching 1 from the left. Just write that out. What does that mean? Well, among other things, it means that x is less than 1. What happens if you subtract 1 from both sides? You get x minus 1 is less than 0. So that's another way you can obtain this negative sign, that x minus 1, yeah, it's approaching 0 as x goes to 1. As x gets close to 1, x minus 1 is going to approach 0. But because of this argument, it's going to approach 0 from the left, because these are going to be negative values. Okay, so when you put that together, now you can say the following. You've got a fraction whose numerator is approaching a non-zero constant, and whose denominator is approaching 0. That tells you that the only suitable answers for this limit are either going to be plus infinity or minus infinity. And to figure out which one, now we can consider the sign. Because if the numerator is always positive and the denominator is always negative, what does that tell you? The fraction is always negative. So that's how you can finally answer it. You're going to get negative infinity. Okay, so that's how we get negative infinity. And pardon me, and that's why this function f has a vertical asymptote at x equals 1, and therefore it has an infinite discontinuity. So this example serves as a way to show you how to detect vertical asymptotes near points without drawing the graph. Okay, we can weaken the idea of continuity a bit and be a little bit less restrictive in the following way. So this is the definition of continuity here. A function, if f is continuous, if all three of these quantities agree. Well, what if only two of them agree? What if we just took that one away and we only considered these two and said we only require that the limit as x approaches a from the left of f of x is equal to f of a? Well, then you get the definition of continuity from the left. And similarly, you could cover this one up. And you could say, what if we only required that the limit as x approaches a from the right of f of x be equal to f of a? Well, then you get the definition of continuity from the right. So that's actually what we're going to spell out here carefully at the bottom of this page. So a function f is continuous from the left at a point x equals a if, when we take the limit as x approaches a from the left of f of x, we get f of a. Okay, and the other analog of that from the right, we just say that f is continuous from the right at the point x equals a, if when we take the limit as x approaches a from the right of f of x, we get f of a. So both of those definitions are just slightly weaker than the requirement that f be continuous at the point x equals a. So in fact, a function f is continuous at the point x equals a in the sense of this stronger definition, if and only if it's continuous both from the left at x equals a and continuous from the right at x equals a. And that's the definition of continuity from the left and from the right. We'll draw a picture in the next clip.